projects. In this video, we are going to explain about the project title Sentiment and Context-Aware Hybrid DNN Attention for Text Sentiment Classification. Introduction. Sentiment analysis of unstructured data, such as comments and opinions, poses challenges due to the vast number of features and the complexity of extracting relevant contextual sentiment features. This complexity arises from the diverse nature of textual content and the need to decipher nuanced sentiments embedded within it. While various DNN architectures have been applied to sentiment analysis, they often treat all features equally, disregarding the importance of semantic and sentiment knowledge. This limitation results in suboptimal performance as these models fail to capture the subtle nuances and contextual cues necessary for accurate sentiment classification. The proposed model represents a significant advancement in sentiment analysis techniques. It introduces a sentiment and context-aware hybrid DNN with an attention mechanism designed to intelligently learn and highlight salient features of relevant sentiment context within the text. By incorporating contextual information and leveraging attention mechanisms, the model can discern and prioritize important features, thereby improving the accuracy of sentiment analysis. In addition to its innovative architecture, the proposed model also employs convolutional neural networks, CNNs, to further enhance its performance. CNNs are utilized to reduce the dimensionality of the feature space and extract local key features from the text. This step helps to streamline the sentiment analysis process and extract relevant information efficiently. Through comprehensive evaluation on real-world benchmark datasets, the proposed model has demonstrated significant improvements in text sentiment classification accuracy. These results validate the efficacy of the model in effectively leveraging semantic and sentiment knowledge, as well as its ability to extract meaningful contextual features from unstructured data, ultimately leading to more accurate sentiment analysis outcomes. Objective. The project sets out to develop a novel sentiment and context-aware hybrid DNN model equipped with an attention mechanism tailored specifically for text sentiment classification. This overarching objective reflects a focus on advancing existing methodologies to better handle the complexities of sentiment analysis on unstructured textual data. One of the primary goals of the model is to overcome the challenges inherent in sentiment analysis of unstructured data. This includes effectively leveraging semantic and sentiment knowledge to extract meaningful contextual features that can accurately capture the sentiment expressed within the text. By addressing these challenges, the model aims to achieve more precise and reliable sentiment classification results. To achieve its objectives, the proposed model integrates several innovative components. Firstly, it incorporates wide coverage sentiment lexicons to identify key sentiment features within the text. Additionally, it utilizes bidirectional encoder representation from transformers to enhance word embeddings, thereby capturing the semantic nuances of the text and enriching its contextual understanding. Furthermore, the model adapts bidirectional long short-term memory (BiLSTM) architecture, a type of recurrent neural network, to effectively capture both the word order and contextual semantic information present in the input text. This allows the model to capture long dependency relations within the word sequence, which is crucial for understanding the sentiment expressed in complex textual data. An attention mechanism is a pivotal component of the proposed model, enabling it to dynamically assign weights to different features within the text. By doing so, the model can highlight and prioritize salient features that are most relevant for sentiment classification, thereby enhancing its overall performance and accuracy. This attention mechanism helps the model to focus on the most informative parts of the text while filtering out noise, ultimately improving its ability to discern and classify sentiment effectively. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This module involves importing necessary Python libraries and packages required for the project. In the context of sentiment analysis, typical packages include TensorFlow or PyTorch for deep learning, scikit-learn for machine learning tasks, Pandas for data manipulation, and Seaborn for data visualization. Exploring the dataset. This module focuses on gaining an understanding of the datasets used for sentiment analysis. It involves tasks such as loading the dataset into memory, examining its structures, checking for missing values, and understanding the distribution of labels or sentiments across the dataset. MR dataset, that is, movie reviews, a dataset commonly used for sentiment analysis containing movie reviews along with corresponding sentiment labels, positive or negative. Rotten Tomato, another dataset of movie reviews with sentiment labels, often used for sentiment analysis tasks. SST2, Stanford Sentiment Tree Bank, a dataset containing movie reviews passed into a fine-grained sentiment hierarchy. SEMEVAL, Semantic Evaluation, a dataset comprising various tasks related to sentiment analysis, providing diverse text data for analysis. Visualization. This module involves visualizing different aspects of the dataset, such as the distribution of sentiment labels, the length of reviews, and any potential patterns or trends present in the data. Seaborn and Matplotlib are commonly used libraries for data visualization in Python. Data processing. Removing the URL and other characters. Regular expressions or string manipulation techniques are used to remove URLs, special characters or symbols that do not contribute to sentiment analysis. Remove punctuations. Punctuation marks are often removed as they do not typically carry sentiment information. Remove stop words. Common words like and, the, and, is are removed as they occur frequently and do not add much meaning to sentiment analysis. Normalization. Text data is normalized by converting it to lowercase to ensure consistency in representation. Tokenization and lemmatization. Text is tokenized, that is, split into individual words or tokens, and then lemmatized to reduce words to their base or dictionary form for better analysis. Vectorizer the text, lexicon-based approach. This involves converting the pre-processed text data into numerical vectors using lexicon-based methods. Lexicon-based approaches involve assigning numerical values to words based on their sentiment polarity using sentiment lexicon. Tokenization. This step involves breaking down the text into individual tokens or words. Keras tokenizer. Keras tokenizer is used to convert text into sequences of integers where each integer represents the index of a word in the vocabulary. BERT tokenizer. Bidirectional encoder representations from transformers. Tokenizer is used to tokenize text and encode it into input suitable for BERT-based models. It typically involves converting text into subword tokens and adding special tokens for padding and separation. Feature selection. Feature selection involves choosing the most relevant features from the dataset that contribute the most to the prediction task. This step includes techniques such as statistical tests, feature importance from tree-based models, or domain knowledge to select the features. It ensures that only meaningful information is used for training the model, reducing computational complexity and potential overfitting. Splitting the data to train and test. This module involves dividing the dataset into two subsets, one for training the model and the other for evaluating its performance. Common ratios for splitting the data are 80% for training and 20% for testing. The training data is used to teach the model patterns in the data, while the test data is used to assess how well the model generalizes to new unseen data. Building the model. Building the model involves defining its architecture and selecting appropriate algorithms and techniques based on the problem requirements. For sentiment analysis, this involves designing a hybrid DNN model with attention mechanism, integrating components like wide coverage sentiment lexicons, transformers, BiLSTM, attention mechanism, and CNN. The architecture is chosen to effectively capture semantic and sentiment knowledge from the text data. Training the model. Once the model architecture is defined, it is trained using the training data. During training, the model learns to adjust its parameters to minimize the difference between its prediction and the actual sentiment labels in the training data. Training involves forward and backward passes through the network, adjusting the weights using optimization algorithms like gradient descent. Flask framework with SQLite for sign up and sign in. Flask is a microweb framework used for building web applications in Python. SQLite is a lightweight relational database management system often used with Flask for data storage. This module involves setting up a Flask application with user authentication functionalities such as sign up and sign in. User data, including usernames and passwords, are stored securely in an SQLite database. User gives input. Users interact with the web application by providing input in the form of text data through the front-end interface. The given input is pre-processed for prediction. The input provided by the user is pre-processed to ensure consistency and compatibility with the trained model. Pre-processing steps include removing URLs, punctuation, stop words, and normalizing the text. Trained model is used for prediction. The pre-processed input is passed through the trained sentiment analysis model to predict the sentiment expressed in the text. The model utilizes its learned parameters to make predictions on the input data. Along with that, we applied LDA model for topic modeling. Latent direct linked allocation, LDA, is a probabilistic topic modeling technique used to discover latent topics within a collection of documents. LDA can be applied to identify dominant topics present in the text data, providing additional insights beyond sentiment analysis. This module involves applying LDA to the text data to extract and visualize topics present in the input. Final outcome is displayed through front end. The final sentiment analysis prediction and topic modeling results are displayed to the user through the front-end interface of the web application. Visualization techniques may be employed to present the results in an intuitive and user-friendly manner, enhancing the user experience. Algorithms used. To implement this project, we have utilized the following algorithms. The first algorithm is LSTM, long short-term memory. LSTM is a type of recurrent neural network RNN architecture designed to overcome the vanishing gradient problem in traditional RNNs. It introduces specialized memory cells with gating mechanism that allow the model to learn and retain long-term dependencies in sequential data, making it well suited for processing text data. In the project, LSTM is utilized to capture sequential dependencies in text data and extract contextual information for sentiment analysis. The next algorithm is RNN, Recurrent Neural Network. RNN is a class of neural networks designed for sequential data processing, where each step in the sequence is processed one at a time. Unlike feed-forward neural networks, RNNs have connections that form cycles, allowing them to maintain an internal state or memory. However, traditional RNNs suffer from the vanishing gradient problem, which makes it challenging to capture long-range dependencies in sequential data. While LSTM and other advanced architectures like GRU, Gated Recurrent Unit, have largely supplanted traditional RNNs in many applications, they still serve as a foundational concept for understanding sequential data processing. CNN, Convolutional Neural Network. CNN is a class of neural networks primarily used for image processing tasks, but can also be applied to sequential data like text. In text analysis, CNNs use filters or kernel to convolve over the input text, capturing local patterns and features. They are particularly effective at detecting patterns in text data, such as n-grams or sequences of words with specific semantic meanings. In the project, CNN is utilized for feature extraction from text data and capturing local contextual information relevant to sentiment analysis. Bi-LSTM CRF, bidirectional LSTM with conditional random field. Bi-LSTM CRF is a hybrid model that combines bidirectional LSTM, bi-LSTM with conditional random field CRF for sequence labeling task. Bi-LSTM captures contextual information from both forward and backward directions, allowing it to effectively model long-range dependencies in sequential data. CRF, conditional random field, is used to model the dependencies between labels in sequential data and ensure the coherence of predicted sequences. In the project, bi-LSTM CRF is applied for sequence labeling tasks such as named entity recognition NER or sentiment analysis, where the goal is to predict a sequence of sentiment labels for each input text. DCNN, Dilated Convolutional Neural Network. DCNN is a variant of CNN where the receptive field of the filters is expanded using dilation rates. By introducing gaps between the filter elements, DCNN can capture larger context while retaining the advantages of local feature extraction in CNNs. DCNNs are particularly effective for capturing hierarchical structures in sequential data, making them suitable for tasks like text classification and sentiment analysis. In the project, DCNNs can be used to capture hierarchical contextual information in text data for sentiment analysis. IWV, Inner Word Vectors. Inner word vectors is a technique used for representing words as vectors by considering their internal structure. Instead of representing words as discrete symbols, inner word vectors represent them as vectors that capture their internal morphological and syntactic features. IWV can improve the representation of rare or out of vocabulary words and enhance the performance of neural network models in tasks like sentiment analysis. In the project, IWV can be integrated into the sentiment analysis model to improve the quality of word embeddings and capture fine-grained semantic information from text data. SAAN, Self-Attentional Aggregating Network, CNN with Attention. SAN is a neural network architecture that combines convolutional neural network CNN with self-attention mechanism. Self-attention mechanism allow the model to focus on different parts of the input sequence, capturing long-range dependencies and improving performance in tasks like sentiment analysis. In the project, SAN is applied to extract salient features from the input text data and capture contextual information relevant to sentiment analysis. SAT BERT, Self-Attention Transformer, SAT BERT BERT. SAT, also known as Self-Attention Transformer, refers to architectures like BERT, bidirectional encoder representations from transformers that rely on self-attention mechanisms for processing sequential data. BERT-based models utilize transformer architecture with self-attention mechanism to capture bidirectional context from input text data. BERT has achieved state-of-art performance in various natural language processing tasks, including sentiment analysis. In the project, SAT-BERT is used as a powerful pre-trained model for sentiment analysis, fine-tuning it on a specific sentiment analysis task to achieve high accuracy. SCAHDNN, BERT bi-LSTM CNN. Sentiment and context-aware hybrid DNN, BERT bi-LSTM CNN. SCAHDNN is a hybrid deep neural network architecture designed for sentiment analysis tasks. It combines multiple components such as BERT or other transformer-based models, bidirectional LSTM, bi-LSTM, and convolutional neural network CNN to capture different aspects of text data. BERT captures contextual information, BiLSTM captures sequential dependencies, and CNN extracts local features, providing a comprehensive approach to sentiment analysis. In the project, SCAHDNN can be used to leverage the strengths of different architectures for improved sentiment analysis accuracy. As an extension, we applied an ensemble method, combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Also, as an extension, we built fronting using Flask for user testing with authentication. Comparison graphs offer a visual breakdown of how our models perform across essential evaluation metrics. Models are compared with the performance metrics, accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is FN comparison graph. On the x-axis, we have FN score, and on the y-axis, we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The model which is performing best among all the other models will be used for prediction. Comparison graphs of MR dataset. In this project, we have also utilized MR datasets. These are the comparison graphs of MR dataset. Comparison graphs of RT dataset. We have also utilized RT dataset, and these are the comparison graphs of RT dataset. The model which is performing best among all the models will be used for prediction. Comparison graph of SEM-EVAL dataset, that is semantic evaluation dataset. These are the comparison graphs of semantic evaluation dataset. We have also utilized SST2 dataset in this project, and these are the comparison graphs of SST2 dataset. The model which is performing best among all the models will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb files. These are Jupyter Notebook files, which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally. At the default address, localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in now. So here we need to enter the username and the password which we have registered and then click on login. We have logged in successfully. So here, click on prediction link. We will execute the project using these data sets. The first data set used in this project is CR, which is customer reviews. The customer reviews data set typically consists of reviews provided by customers for various products or services. Each review is accompanied by a sentiment label indicating whether the sentiment expressed in the review is positive, negative, or neutral. This dataset is commonly used for sentiment analysis tasks where the goal is to classify the sentiment conveyed in a given text. And the second dataset used in the project is MR, which is movie reviews. The movie reviews dataset comprises reviews of movies usually obtained from websites, forums, or other sources where users discuss movies. Similar to the customer reviews dataset, each review is labeled with its sentiment polarity, positive or negative. It's another standard dataset used for sentiment analysis and text classification tasks. And the third dataset used in the project is RT, which is Rotten Tomatoes. Rotten Tomatoes is a popular website that aggregates reviews and provides ratings for movies and TV shows. The RT dataset refers to a collection of reviews from Rotten Tomatoes where each review is annotated with a sentiment label indicating whether it's positive or negative. Like the CR and MR datasets, it's utilized for sentiment analysis tasks. And the fourth dataset used in the project is SEM-EVAL, which is semantic evaluation. Semantic evaluation is a series of workshops focused on the evaluation and comparison of computational semantic analysis system. Semantic evaluation provides data sets and tasks covering various aspects of natural language understanding, including sentiment analysis, semantic similarity, word sense, disambiguation, and more. Participants in SEM-EVAL competitions develop systems to solve specific NLP tasks using the provided dataset. And the fifth dataset used in the project is SST2, that is Stanford Sentiment Tree Bank. The Stanford Sentiment Tree Bank is a dataset introduced by researchers at Stanford University. It consists of sentences extracted from movie reviews, where each sentence is labeled with its sentiment polarity, either positive or negative. The sentiment labels in SST2 are derived from the overall sentiment of the movie review. Additionally, SST2 provides a tree structure that represents the sentiment compositionality of sentences allowing for more nuanced analysis. By using these data sets, we will execute the project. So here we can see a prediction link. We can execute the project using these 5 data sets. First, we will execute the project using the CR data set. So click on CR data set. So here we need to enter the message. After entering the message, we will predict the sentiment for the message, whether it is positive or negative. So here I'm entering the message. This is the message which I have entered. Now click on predict button. So here we can see the message which we have entered, and the label for the message is the review is negative. The topic for the paragraph is most dependent upon these words. Let us upload one more message. Click on prediction link. Now click on CR dataset. So here I'm entering one more message. This is the message which I have entered. Now click on predict button. So here we can see the message which we have entered, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. These words make the message positive. Now again, click on prediction link. We will execute the project using the second dataset, which is MR. So click on MR dataset. So here I'm entering one message. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. Let us enter one more message. Click on prediction link. Click on MR dataset. So here I'm entering one more message. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. Now click on prediction link. We will execute the project using the third dataset, which is RT dataset. So click on RT. So here I'm entering one message. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is excellent. The topic for the paragraph is most dependent upon these words. Let us enter one more message. Click on prediction link. Click on RT dataset. So here I'm entering one more message. This is the message which I have entered. Click on predict button. Here we can see the message, and the label for the message is the review is not bad. The topic for the paragraph is most dependent upon these words. Now click on prediction link. We will execute the project using SEM-EVAL, that is semantic evaluation dataset. So click on it. So here I'm entering one message from the semantic evaluation dataset. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. Let us enter some more messages. Click on prediction link. Click on semantic evaluation dataset. So here I'm entering one more message. This is the message which I have entered. Now click on predict button. Here we can see the message, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. Now click on prediction link. We will execute the project using the SST2 dataset. So click on it. So here I'm entering one message from the SST2 dataset. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is negative. The topic for the paragraph is most dependent upon these words. Let us enter one more message. Click on prediction link. Click on SST2 dataset. So here I'm entering one more message. This is the message which I have entered. Now click on predict button. So here we can see the message, and the label for the message is the review is positive. The topic for the paragraph is most dependent upon these words. By using these data sets, we have predicted the sentiment for the text as either positive or negative. Now click on sign out button here. The conclusion of the project is the core claim of the project is that the proposed sentiment and context aware hybrid DNN model with an attention mechanism brings about a notable enhancement in the accuracy of existing text sentiment classification methods. This implies that the model outperforms previous approaches in accurately discerning and categorizing sentiments expressed in text data. The model's effectiveness stems from its ability to leverage semantic and sentiment knowledge adeptly. By intelligently extracting relevant contextual sentiment features from the text, the model ensures that it captures the nuances and subtle cues embedded within the data, leading to more precise sentiment analysis outcomes. The model integrates various cutting edge techniques and components, including wide coverage sentiment lexicons, bidirectional encoder representation from transformers, BiLSTM, attention mechanism, and CNN. Each of these elements contributes to different aspects of the sentiment analysis process, such as capturing word order and contextual information, assigning weights to features, and reducing feature space dimensionality, thereby enhancing the model's overall performance and accuracy. In addition to the model's technical advancements, the project also emphasizes the importance of user experience by integrating a user friendly Flask interface with secure authentication. This ensures that users can interact with the system seamlessly and securely, ultimately enhancing their overall experience during system testing and evaluation. The effectiveness of the proposed model is empirically demonstrated through rigorous evaluation on real world benchmark datasets. By showcasing significant improvements in sentiment analysis accuracy compared to existing methods, the project underscores the practical applicability and relevance of the proposed model in real world scenarios, thereby validating its effectiveness and impact.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.